So the title has quite a few words. First, at some point, we want to talk about active wake mixing for downstream turbines. So active wake mixing is going to be our first keyword. To do that, we need wind speed estimations. And once we do, we can do synchronized helix control, because our focus here will be mostly on the helix, but we'll still talk a bit about the pulse. And these three, I would say, sections will really guide us throughout the presentations. Luckily, I'm talking to task 44, wind farm flow control. So I guess the first part on active wake mixing, I can go quite fast, and I will spend a bit more time on wind speed estimation. You can notice I put robust here. Robust is always a tricky word to use when you talk to control people. So I hope at the end you agree with me on at least the definition I use for it. And then I will talk about synchronizing helix control for downstream turbines. With active wake mixing. So for active wake mixing, we typically have two types of techniques that are out these days. I would say we have the pulse and we have the helix. And those control are typically done by having pitching loads which are pretty basic. So they use a fixed frequency, which is provided by a Strual number, so fixed Strual pitching law. For the pulse, we use collective pitch control, and this generates those pulsatile patterns that you see in the wake. And for the helix, we use individual pitch control, which will eventually generate those lateral motions. And here you just see a slide, but the motion is up-down also. So the wake basically propagates as a helix, hence the name. And for those that know me a little, you know probably that I really like those laminar flows because I think they're so elegant and so beautiful. But unfortunately, real life is turbulent, or fortunately, I don't know. That's a matter of perspective. But so we already have pre-existing. So here you see that those controllers, they generate large-scale structures in the wake. But in real life, in turbulent conditions, we already have pre-existing structures that actually hit the turbines. And those structures, they can, for example, generate meandering naturally without you doing anything at the turbine. So there's kind of a question on those control here that are dynamic. How do they interact with what's already present in the wind content that's hitting it? So that's a first thing. And even further, if you now imagine that you have a downstream turbine located here, how does the control of a downstream turbine interact with these very specific wakes that are hitting? And so one of the questions I think that is really present in this active wake mixing community is, can we do better than open loop fixed rule pitching? And can we do it also on downstream turbines? And if so, how do we extend to deeper arrays? And I think you can take it through any way. At some point, you will come down to the fact that you need to know the wind. And you have several options. The most basic one to know the wind that is impinging is probably to use an anemometer, but that might be a little poor in terms of the information you get. The other one, if you're lucky enough, you might have a lidar mounted on the nacelle, and then you get plenty of information. It's very comfortable. Now, if you have an in-between, you don't want to add an instrument onto your turbine, but you do have blade load sensors, then you can consider that actually your blades operate as sensors because you measure the forces that are exerted on them. So you have a reflection of the wind speed, and you can out of those blade loads, estimate the wind. And this is a trend that we've also seen emerging in the community to really use rotor as sensors of the flow. All right, so that was for active wake mixing and a bit of the context. And now you've seen that I've already taken kind of my option on how I'm going to be knowing the wind. And so I take you right away to the second part, so the wind speed estimation. And for that, I'd like to highlight that the work was done when we were still young PhDs with Maxime Lejeune back at EC Louvain. So I'd like to really acknowledge his contribution in this part of the work. So the idea here is really that we're going to use blade load based wind speed estimator. So we measure the loads on the blades, and out of that we try to reconstruct the wind speed that is impinging on the rotor. The way we do it then is we have our system, which is the wind turbine with the wind. This system is control, and at the end of the day, what we want to reconstruct is the wind characteristics. And one option to do it, and we started with that work from Batasso in 2018, was to use estimators here that are based on extended common filters. to estimate from the measurements of the out of plane bending moments to estimate blade effective wind speeds. So for each blade that we have, we're going to measure the out of plane bending moment and try to reconstruct using an extended common filter the blade effective wind speed. So long story short, the big block here is an extended common filter that uses BEM as an internal model. Now, for the people that don't want to know more, you can take like a 2 minutes break. For the people that want to know a bit more, here is what's behind the block. So the idea of those common filters is always that you try to estimate something. Here, we want to estimate the wind speed. And we're going first to, so if we start from the estimation that we had at the previous time step, we're just going to propagate it in time and say, okay, I have a certain understanding of how this quantity here should evolve in time. In our case, we go very simple, and we learned from the work that was proposed in the work of Botassa. We say, okay, if I look at the wind speed impinging on one blade at one given instant, I just move a little bit, my blade effective wind speed shouldn't change too much. So my propagation model is very simple. Wind speed now is wind speed before. And then I take this prediction of the future estimate and I throw it into a model of my system. And this model will in turn tell me for this wind speed and this turbine and this blade, I will get this bending moment. And this bending moment I can compare with what I measure on the turbine. And the comparison between the two is supposed to tell me how good my prediction was. And based on the difference between the two, I can correct my estimation and get I can correct my prediction and get a proper estimation of the blade effective wind speed. And as I said before, what you need here is to have a measurement model. You can use a linear model, for example. That's, I think, what was originally done. And then you don't have an extended common filter. You just have a linear common filter. The problem is that the moment you're out of the linearization point, your model becomes not as accurate. And we're going to be talking about the pulse and the helix. So this guy here, the pitch angle in our controller, is going to be moving quite a lot. So linear model here is a bit tricky. And that's why we decided we would opt for a BEM model that can run very quickly and provide us for a given wind speed, given rotation speed, and given pitch angle, the bending moment that we should observe on the blade. All right, long story short, that's an EKF with a BEM as an internal model. But the question is, so if I come back here, we use the bending moments and the operating parameters here to estimate the effective wind speed that then we use for reconstruction of the wind field. The thing is that when we do the pulse and the helix, as you can see here, we actually change those pitch angles quite a lot, but mostly our bending moments are really effective. And so there's kind of a question on, okay, can my estimator actually still be reliable when I'm pulsing or when I'm helixing on the turbine? Can it still provide estimations that are good enough? And that's what we wanted to test. And either we can test on real turbines, but I was not lucky enough to be provided with those. So what we decided to do is to go for numerical simulations and consider that our real life would be LES simulations that you see just here. Yeah, so we were kind of nice. We used the NREL 5 megawatts, so we don't have lots of flexibility and we didn't model it. We have underrated wind speeds because we want to reproduce conditions where typically we would apply the helix or the pulse, and we have an intermediate turbulence level. And what we're going to do is that we're going to apply on T1 here a baseline control, the pulse, and the helix. And we want to make sure that T1 is still able to estimate what's coming onto it equally, whatever it's doing here. And we also have an interest in T2, because remember, I started by saying at some point we want to do synchronization of T2 here with the pulse or the helix wake. So we also want to make sure that when those kind of weird wakes, the pulse or the helix wakes, are hitting T2, T2 is still able to estimate properly too. All right. There's always a question when you want to do wind speed estimation is you're going to do your estimate with your estimator, but what do you compare it to? And so you could say, okay, I will take the wind speed that is here, like 1D or 2D upstream out of the induction zone, and then convect it and compare the signals. That's always a bit tricky. So what we decided to do is to say, okay, for T1, we're just going to run the exact same simulation with no turbine at all and just sample the flow field here. And that's going to be our reference wind speed, our ground truth wind speed. And for T2, we're going to do the same thing, but we need a wake coming upstream. So we're going to simulate the same case, but with T1 only. And so as we want to have baseline, helix, and pulse, we need to have those T1 only simulations for baseline, helix, and pulse. And then we get our reference wind speed for T2. All good. And these are the results that we have. That's a lot of graphs and a lot of colors. So maybe I'll walk you through this slide. So the first thing that you see is the reference, so the black line here, so what I just described. And you see, so time domain and frequency domain of the signals, and you see two types of signals. You see the rotor effective wind speed. So out of our 3 blade effective wind speeds, we reconstruct the mean, the rotor effective wind speed. But you also have sector effective wind speed. And so here it's the upper part of the rotor. That's what you see here. So we use the fact that the blade is rotating and we know it's azimuth to actually attribute the blade effective wind speed to a sector of interest. And that's what you're seeing here. The first thing that is probably striking is that between the reference and all our control cases here, so this is our reference and these are our estimates when the turbine 1 is doing baseline IPC, helix, or pulse. We also tested IPC, though I won't low delay aviation IPC, but I won't talk too much about it today. The first thing that is striking is that we have a bias in the estimation. So that indicates that between the blade loads that we measure from the LES and what the BEM gives us as an estimation of what we should get, we have a difference. So we'd have a difference in models, and this is the reason why we have this bias. So for the control people in the room, I think there are many strategies to tackle those biases, and I'd be happy to leave that to you. I have to say that I was mostly interested in the fluctuations. What it's like, do I see a gust? Do I see a lull passing by? And so in that sense, what we cared about is mostly those fluctuations than the absolute value. And you see that those fluctuations are pretty well captured for baseline, helix, and IPC. For pulse, however, we see that the turbine considers that the wind speed is doing this here. And this here appears exactly at the period at which we do the pulse. Now, that's why we also put the frequency domain graph, because when you look at it here, you should have basically no spike here, no specific spike at the pulsing frequency. Yet for the pulse, the turbine has estimates that the incoming wind is having those oscillations. So that's an issue for our estimator. For the helix, it feels like it's doing right when you look at just the rotor, but when you look at the sector effective wind speed, actually you also see this periodic pattern appearing, and same when you look at the PSD, you really see this happening here. And of course you don't want to have that, because again, because I'm pulsing or doing the helix doesn't mean that I get to influence the wind in front of me. All those signals should just be the same line. And so the reason for that, the reason we attribute is the model. We use, at some point in the common filter, we compare measurement with an output of the model, and the model is the BEM in our case. But one of the fundamental hypotheses of the BEM is that it considers that the wake is fully developed. So it considers that the inductions are stabilized. And what we're doing here is that we're constantly changing this beta here, this pitch angle, all the time with the pulse and the helix. So our inductions here, A and A prime, never get to stabilize. So actually what we're doing, I won't get very much into the details of this slide, but we can come back to it in the questions. What we're doing right now is considering that with the static BEM, the moment we actuate the blade, immediately we get the load response. And that's not true. And as we consider it true, we generate parasitic errors in the estimates at the pitching frequency. So the solution we propose to tackle this issue is to actually use a dynamic correction in the BEM computation of those inductions. And for the correction, we didn't go anything fancy. We went for what is offered in the literature. So little flashback, this was our estimator in the first place. This is now what our estimator, what we believe our estimator should look like in order to be able to deal with those dynamic pitching that we have at the rotor. So this was the curve that we had just before. So high frequency content for the pulse and for the helix when you look at sectors. Now, when we go from static to dynamic BEM as internal model of the estimator, we see that we really kill this peak. So, and that all our estimates here are pretty much on the same line. So this is what we consider as a robust estimation. The estimation is robust to the control strategy that you apply on your turbine. It doesn't care whether you're doing the helix, the pulse, or if you're just operating baseline. And that, of course, is really good if you want to do control in terms with based on those wind speed estimates. So that was for the first turbine. Now, as I said before, we have an interest in the second turbine. And if you look at the rotor effective and the sector effective wind speeds at the downstream turbine, for the baseline, the pulse, and the helix, in that case, when you have the pulse and the helix, you do have in your wake an added frequency content. And we really want to see that one, to capture that one, in order to be able to synchronize the wakes further downstream. And actually, you see that in this case, the estimator is able to do so. So the estimator sees this peak here that we have both at the rotor and at the sector level when we have the pulse or the helix active on first turbine, and we estimate the wake from the second turbine, seen from the second turbine. And this, of course, as I said, is really good news because at some point we want to synchronize with the downstream turbines. And so this takes me straight to the third and last part of the presentation. I will take a sip of water and let you breathe for a second. All right, and for this work, this part of the work, I want to acknowledge Mees van Wondelen that was really leading this part of the research on really using those estimators. He's tried many forms of estimators to do this synchronization. And you see that here we have a bit of a bias and we opted for synchronizing helix wakes. So probably the door is open to synchronize pulsing wakes. And before I dig a little bit deeper into the synchronization algorithm, if I may call it like that, I just want to look back a little bit. So what we're talking about is a configuration where we have 3 turbines. T1 is doing the helix for the moment. T2 is doing baseline, so its wake just goes kind of straight. And T3 just receiving the wake of T2. And what you do when you're doing the helix control is that you apply this perturbation on the first rotor that is rotating over time. Typically, the way you can see it is you take, using the IPC, you offset the center of the thrust vector, and then you make this rotate over time. And this perturbation that you generate at T1 actually has an effect on the wake. And so when the wake is hitting T2, there is this additional periodic component that you're seeing. Now, the idea with synchronization is to say, okay, we also want T2 to do the helix. And there's actually a fun question is, how do you phase the moment that you perform your helix on T2 with respect to the incoming wake? And that's where we need an estimation. And that's where you're going to see the link with what we did before. But before I dig a little deeper into that, I think it's always good to come back to what everyone doing IPC really loves to use as a transform. It's the MVC transform or the Coleman transform. So the idea, for those who may not be familiar, is really that we can map any quantity from the blades, the rotating blade, to the fixed frame. So in this case, I think the most common, the one that is the easiest to understand is like I have out of plane bending moment on a blade. That's what you see here. So this is the axis of the force. So you're just like pushing the blade out of plane. Or 3 blades, and by going through the transform, you can turn that into a tilting moment. If you have an overload on top of your rotor, you have a positive tilting moment, and if you have an overload on the right side of the rotor, you're going to have a positive yawing moment. And this transform you can use back and forth, and so you can also say that if you know the collective bending moment plus the tilt and the yaw bending moments, then you can come back to the blade bending moments. And so This is typically for the forces, but you can say the same about the pitch angles. So you can define your individual pitch angles, but maybe it's easier to just define them in the fixed frame, so a tilt and a yaw pitch angle. So if I'm here, my blade is passing through this axis and it starts pitching, it's going to create a left-right imbalance. And so I'm going to create a yaw moment, and same if my blade goes all the way to the top. And again, you can go from one to the other. The reason I'm taking 2 minutes to remind you of that is because that's how the helix is formulated actually in terms of control. So the helix on T1 is always formulated as a sine and a cosine perturbation on the tilt and yaw pitch angles that in turn generate a sine and a cosine perturbation on the tilt and yaw moments of the turbine. And these sine perturbations are generated at a given frequency, omega e, which is determined by the Struhl number. And here we use standard Struhl numbers 0.25, 0.3, as we commonly see in the literature. So that's one thing. And so the hypothesis that we have for this work is to say, okay, I have this perturbation here that I'm generating at the turbine, and this in turn will come down to a change in tilting wind speed and yawing wind speed at the second rotor. So I will actually retrieve the same kind of signal with a certain offset. That's the offset that you see here between my actuation at T2 and the moment it hits me, my actuation at T1 and the moment it hits at T2. And if we were living in the world of solid mechanics, this would be correct. We would just like propagate this perfectly and have just this phi. So the wave would propagate as a solid at a given frequency. Now, unfortunately, or for more fun, we live in the fluid dynamics world. So there's quite a lot of flexibility and deformation that's going to happen in this helix. And so in order to enhance a bit, to provide a bit more flexibility in the way we formulate the problem, Mace decided to opt for a phase in the tilt and a phase in the yaw component. And eventually, so that tells us that's the way we kind of model U tilt and U yaw. That's the way we model the incoming helix that is hitting the turbine. And basically what we want to do is track those phases. And by tracking those phases, what we mean is that we want to synchronize the helix. So we want to provide it a sine at the given frequency, taking into account this offset or this phase, sorry, of the incoming helix. And on top of that, you can decide that either you want to be sharp on top of your helix or that you want to be here or there, etc. So you can decide for an offset between your incoming wake and the actuation that you're going to impose on T2. And that's what you see here with the fancy animation. All right. Now there's just an issue, is that here, flashback number 2, what we used was the BEM. And the BEM doesn't know this U tilt and U yaw thing. Like that's what we want to estimate, but the BEM doesn't know any U tilt or U yaw. What the BEM knows is the blade effective wind speed. So we need at some point to like transfer and make them speak. But again, flashback number 3, that's the last one, because 1, 2, 3 is fine. Then it becomes a bit boring and repetitive. So that's the last one. We can map, thanks to the MBC, any tilt yaw quantity to a 1, 2, 3, blade 1, 2, 3 quantity. So if we could do it for the moments, we can actually also do it for effective wind speeds. So what we're going to do is that we're going to have our tilt and yaw wind speed, map them back to blade 1, 2, 3 wind speed so that we can speak to the estimator. The estimator can speak back to us, and we get to estimate those phases of the incoming helix. So that's a lot of information, and if I had to sum it up with even more information, that's a whole scheme of actuation. I'm not sure I'm going to go through it, or maybe very quickly. So we have the turbine here. So that's the second turbine. It sees a certain perturbation. This perturbation exerts results in bending moments. Those bending moments are mapped to the fixed frame using the MBC transform. And they are compared with the fixed frame estimated bending moments from our estimator. And the comparison of the two helps us correct our estimation of the phase of the tilt and yaw phase of the incoming helix. And these tilt and yaw phase of the incoming helix is what we use for the synchronization controller based on an offset that we are free to choose. So that's the long story short again. And after all these conceptual ideas, it's time to just go and see how this works. And again, I will take a sip of water and let you start with the slide. So here what Mace used to demonstrate this controller is the MR code, coupled to open fast. So here the turbines are flexing, and they're 15 megawatts turbines, so they're flexing quite a lot actually. They're also involving in a neutral boundary layer with a reasonable turbulence level, 3 to 5%, reasonably low. And also to make sure that the helix is quite visible, we went a bit high on the amplitude, so the helix is pitching with a 4 degrees amplitude. And this is typically the flow fields that you observe, and these are phase averaged, and on top of the flow fields you see the wake center lines. And so in terms of the controllers, kind of our new baseline or our new reference is we do helix on T1, baseline on T2, and baseline on T3. And then we're going to compare that with having helix also active on T2. And we're going to try a certain number of phases. So we're going to try to just be in phase with incoming helix, or a bit further on the opposite side, etc. And these are typically the results that are obtained by Mace. So what we see here is the results. So the gain or the loss in power with respect to this case here, to our new baseline case, from using the synchronization of on T2. And so what we see is that globally, when we start pitching on T2, we lose power. That's something we know. When we do the helix on a turbine, we lose a little bit of power. Though it's interesting to notice that depending on your phase, the phase offset between so your incoming helix and where you pitch on the phase, you're going to get different power losses. So that's something to take into account. But mostly for the third turbine, because in the end, we do all of that to benefit the third turbine. And what we see is that, again, we have a strong S shape here. So there is a peak frequency, a peak offset, sorry, where we extract the max power for T3, or when we propagate the max power for T3. And when you put it all up for T2 plus T3, these are typically the gains or losses that you obtain. So one thing that is important, like the takeaway out of that, I would say, is this was only made possible because we had the robust estimation with the DIN-BEM. So we also tried not using the DIN-BEM in the estimation, and it didn't work because every time we would change our offset here, we would change the reaction of the turbine. And so our estimation of the incoming phase here was not consistent. So that's first message. And the second message is really, if you want to do active wake mixing on downstream turbine, you have to be careful what you do, because if you don't pay attention, you might end up in that zone here where you actually lose power instead of creating more power for the T2, T3 pair. But if you're good enough, then, good enough, if you're choosing your phase wisely enough, then you can be in a zone where you get even more power downstream. What of course we want to understand a bit better, and that's still future work. Oh yeah, so that's going to be hopefully submitted soon, and Mace is also going to present that work in Win Europe. So that's also why I don't want to get too much into the details and not spoil too much the work, but just maybe a perspective, an immediate perspective for us. That's still something we're working on. So here you see the different cases. So a case where we only have the first turbine, just to show you, how the wake propagates downstream. And then you have here T1, T2, 3 with different phases on the second turbine, different phases of the helix. And yeah, we're still willing to fully understand what is happening and why one case is better than the other and how it works and what happens to the wakes, etc. So this is a little bit of a teaser for future presentations that you'll probably see around from Mace. And with that, I think it's time to come back to this slide that you've seen a few times already. So I started with active wake mixing. Can we do better than open loop fixed rule pitching low? And I think we can. I think it's also something to investigate for downstream turbines. But the conclusion that I drew in the first place was we need to know the wind. And to know the wind, we decided to opt for wind speed estimation. And we actually had to pay a little bit of attention to the fact that we're doing with the pulse and the helix dynamic things on the turbines, and the usual models that we use in our estimators are probably not sufficient. So we need to be careful what models we put in our estimators to ensure that our estimation is not biased, is not made inaccurate by the controller that is active on the turbine. And then once we had that robust estimation, we were able to use the estimation to first use the blade effective wind speeds, formulate the helix wake in terms of those blade effective wind speeds with the U tilt and U yaw, etc., and go to the control of the second turbine. So with that, I will conclude. I hope the title is now clear for everyone. And once again, I'm the one given the spotlight today. But without all these people around, this presentation wouldn't just be there. Those results would just not be there. And people is one thing, but also funding is another one. If you have no money, you can do no research. I think that's important to remember. And you see the number of universities and institutions that were involved in this work. And last thing, when we're not given real turbines, we're really happy to do numerical simulations, and that also requires resources. And once again, you see there were quite a few supercomputers used for this work. So now I think it's really time for me. I hope the Americans are now well awake and the Europeans are still awake. And Yuri, I think I'll just leave the floor to you. Thank you.
Thank you, Marion. Great presentation. Super interesting work. We have about a little under 10 minutes for questions. So if you have a question, just raise your hand, and I guess I'll start. So on slide 15, I think it was. Can we go back to that?
Yeah.
Yeah. So here on the right bottom plot, which shows the PSDs, you see like a peak at the excitation frequency at the helix for both the full wake and the section, right?
Yeah.
It's kind of a little bit counterintuitive to what I would be expecting, because I would be expecting that the helix, like if you look at the full wake, like over the entire rotor, it would be more or less constant. Whereas if you look at a section, it would be, you would clearly see this peak, similar to how you saw it at the upstream turbine. So can you maybe elaborate a little bit on why you also see this peak at the full rotor?
Yeah, so I feel that if you run the helix, like in the very first simulation I showed, no turbulence, no wall, nothing, then indeed, mostly what you're going to do is force the wake to like be displaced and just rotate over time. So if you take a rotor in the center and compute the average wind speed there, you shouldn't really see a peak. Now, I believe that what we see here is also the effects of, so we have shear, or so the wake is constrained and it's not just doing very kind circles. And so you see that the peak is not as high for the rotor effective than for the sector effective, but still there is a peak, and I would say at least this is my answer to it.
Okay, yeah, that makes sense. Thank you.
Thanks.
Go ahead, Marion.
I think Mario Rotea can go. Yeah, perfect.
Yeah, thank you. That was a great talk. I appreciate the simplicity and the depth of the work. I have a question about the offset for obtaining power gains. Is it a function of a mean wind speed?
Wait, sorry. Can you repeat the question?
Yeah,
I'm not sure
the offset. Let's go to one of the the offset that you picked in order to realize the gains in the cascade of three turbines. Let's go to one of the plots at the end. Keep going.
This here? That's what we're talking about?
That one. Yeah.
Perfect.
Are those three plots a function of the incoming mean wind speed?
No, that's the gain. That's the delta of power for the turbines. That's not wind speed. That's really power at the turbine, extracted at the turbine.
Yeah, my question is, if I pick the phi offset from this plot, which you did simulations at 8 meters per second, will that work at 4?
This I cannot tell you. I wish I could extrapolate from 8 to 4 and from 8 to 12, but no, I can't. So I hope that we get the same trends, but the numbers exactly, I think they are dependent on the wind speed.
Okay, that's all. Thank you.
All right, thank you.
Eric, go ahead.
Yeah, very nice presentation. Thanks. I was wondering for the dynamic inflow model for the wind speed estimator. Maybe I missed it, but did you have to tune the time constant for that model, or just use like a best practice value, or?
No, so at first I started with best practice value, and then I realized that it was not probably the best. So I tuned against the LES. So maybe I can show this figure here. So what we did was running then very simple LES cases, because in the LES we don't have this problem, like the changes in induction are computed by the LES naturally. So what we did is constant inflow, like uniform inflow, no turbulence, whatever. We do the pulse, the helix, so we get the rotation speed of the turbine, the blade pitch angle, and we get the induction at all the positions of the blade, and same, we get the bending moments. And what we did was comparing the static BEM, which is the dashed line here, and you see that here the static BEM is really off, and then we played with the time constants in the model such that the dynamic BEM would match the LES. And you see that it's not yet a perfect match, but at least for then the estimation, which was what we cared about, it was good enough.
Yep. Okay, good. Thank you.
Thank you.
So related to this, Marion, I also have another question. I think if you go back like maybe probably one slide, like where you have your
here?
like already no, it was like where you have your control scheme with the Camel filter
and like this one here?
Yeah, like that one.
All right.
Yeah.
I will remove that because I guess you're interested in what's in there, right? Yeah.
Yes, exactly. So so my question is like you have your system on the left, which is your turbine, but you're running simulation, so your system is also some sort of model, right? So how does your measurement model, your BEM model, compare to your system, and how does that extrapolate to if you would use this on a real turbine?
Yeah, that's a really good question. So once I had the question, why don't you have the exact same, if you use the same polars for your BEM and your LES, how is it that you don't have the same measurements for the same input wind speeds? So why do you have a difference in the models? That's intrinsic to the fact that on how you compute, you might have the same polars. You don't compute the blade loads equally when you use a BEM or when you use the LES because of all the sampling of the wind speeds. Now, what I would say is that at least in terms of the system, when we use the LES, all those dynamic effects appearing at the blade, we're able to capture. With the BEM, it's always like you see, it's just basically a filter on the inductions. So I would trust that better and believe that this is closer to my reality for sure. Also, in terms of the inflow that you can provide here, we can really have like turbulent inflows, wakes, shear, sorry. For the BEM, it's another story. So
do you believe that if you would use this exact same scheme, like obviously you would need to sort of retune maybe some parameters, but that would also work on a wind turbine?
I think we would have to do quite a bunch of filtering for the bending moments for sure. But yeah, I hope so. I think one of maybe what I see as the biggest challenge is that, I mean, it's easy to do the BEM of the NREL 5, right? We have all the properties, we know it, we have the validation, everything. For a real turbine, that means you need to also have all this information. So if you have a nice turbine manufacturer with you, probably you can get it. If you don't, that can be a limit. So yeah.
Great. Thank you.